Welcome to this lecture on transition metal organometallic chemistry from principles to applications. We have been discussing a very important topic in this course over the last few lectures. In the last lecture, we have been speaking about Ch activation. Ch activation is an important area of research in organometallic chemistry and has tremendous potential for academic as well as industrial applications. Now, what we discussed in our last lecture was how many types of Ch activation methods are known, and in that context we looked at intramolecular Ch activation reactions. We also discussed at how this Ch activation reaction proceeds, and what we saw was that Ch activation reactions originates with agostic Ch M kind of interactions. So, in our last lecture what we had seen is the methods of for Ch activation reactions, and in particular we have discussed examples of an intramolecular Ch activation reaction We have also came across agostic M type interactions. These agostic interactions are at the source of Ch activations, and hence they are of importance and they are useful. And what we have also looked at evidences for agostic interactions. This involves various spectroscopic techniques like proton NMR, carbon 13 NMR, IR, as well as X-ray and neutron diffraction studies. So, what we discussed in the last lecture was the fact that Ch activation initiates at agostic interaction, and that agostic interaction weakens the Ch bond and does not really fully cleave it, and that weakening of the Ch bond can be observed in the spectroscopic signature of various spectroscopy like the proton, carbon, IR, as well as structural characterization using X-ray and neutron diffraction techniques. Now, between the types of Ch activation, we have spoken about intramolecular Ch activation, and in today's lecture we are going to talk something more interesting and more difficult, which is intermolecular Ch activation. So, in this lecture we are going to look at intermolecular Ch activation and how this proceeds. Now, as for the intermolecular Ch activation, examples of such activation was long known for aromatic substrates. It is important to note that for the intramolecular Ch activation, we too have also looked at a similar aromatic substrate, whereby a Ch bond underwent activation intramolecularly. in our as discussed in the last class. Also for as for intramolecular CH activation, the prerequisite criteria was that the metal complex has to be electronically as well as coordinatively unsaturated. The same holds for intermolecular CH activation, where the metal complex has to be both electronically as well as coordinatively unsaturated to undergo such CH activation. This is illustrated in this ruthenium complex. So, this has 16 valence electrons and hence electronically unsaturated. And also the coordination number is 4 and hence coordinatively unsaturated. So, this complex fulfills the criteria for CH activation. So, when treated with naphthalene, again a aromatic compound, intermolecular CH activation is observed and the product obtained is this CH activated product and ruthenium is bound to this naphthalene moiety as well as the hydrogen. So, here the activation of a CH from this carbon and this hydrogen has happened as a result of oxidative addition. Hence, the coordination number now has increased to 6. So, it is become coordinatively saturated and the valence electron is, it has become 18 valence electron complex. Thus, this has become saturated both electronically and coordinatively. So, the basic criteria for CH activation is common for what was there existed for intramolecular CH activation reactions. These are commonly observed for aromatic substrates as is seen over here, and that this proceeds via oxidative addition on a complex which is both electronically and coordinatively unsaturated. As a result of this intermolecular CH activation, the final complex usually is a ruthenium aryl hydride complex, as the CH bond of this arene got activated, resulting in a electronically as well as coordinatively saturated 18 valence electron compound having coordination number of 6 as shown over here. Now, with these several other examples of CH activation became prominent. Now, what is important is to move beyond. So, the utility of CH activation was further realized in terms of CH functionalization, which proceeded after CH activation. So, let us take a look at how CH activation is very difficult because of strong CH bonds and its selectivity is a issue. And ubiquitous nature, very challenging. Now, what we saw that this initiates with CH M agostic interaction, this CHM agostic interaction weakens CH bonds, but does not cleave it. Now, it is up to this far that we have been seeing, we have seen examples of both type, intramolecular as well as intermolecular CH activation. Now, what I am going to talk about is something beyond this agostic and CH activation, and something utility wise very significant is that after the CH activation has happened, one can achieve CH functionalization. Now, CH functionalization is a very important step whereby this hydrogen of this CH bond after activation get replaced with a functional group. So, what it means is that CH functionalization gives CFG bonds or groups. So, what has been achieved by this is that the hydrogen has been replaced by a functional group, and hence CH functionalization is a very important area of organometallic research. Now, as we see, if we take a look at the whole perspective, that this CH activation, it's like it starts with a CHM type agostic interaction leading to CH activation and followed by CH functionalization, where the hydrogen is replaced by a functional group. Now, this can be done catalytically, this can be done stoichiometrically, and this is of immense interest to both industry as well as academia alike. Why it is interesting to industry? Because it helps produce different value added substrates if I can functionalize the CH bonds, and that can lead to various valued commodities that we use in our day to day life. And it is also important from academic perspective because it throws open a very challenging intellectual problem that one has to solve with regard to carrying this functionalization, that one has to break a strong CH bond and also one has to achieve selectivity in this ubiquitous CH bond that are always present. Now, the first and the pioneering work in this area has been done by Shilov, who has shown the first example of CH activation followed by CH functionalization, whereby he had achieved the CH activation in a catalytic fashion and CH functionalization in a stoichiometric fashion. So, Shilov put together the whole concept in terms of chemical catalysis and achieved all the way from CH activation to CH functionalization, in which the first part was achieved in a catalytic fashion and the second part was achieved in a stoichiometric fashion. Let me illustrate this pioneering work of Shilov through the example that has been studied. So, this platinum complex bis aqua platinum chloro moiety 2 water 1 chlorine platinum plus binding and activating a methane molecule So, this is formed from the cationic fragment Pt plus by reacting with methane. And this, what is observed is an agostic interaction. Type So, what one can see is that this cationic platinum complex reacts with molecule of methane, leading to the first agostic type interaction in form of platinum interacting with CH bond of methane in the cationic species. Now, this compound, as a result of this agostic interaction, the hydrogen becomes acidic in nature and eliminates a proton giving rise to this neutral platinum methyl complex. Now, this neutral methyl complex can be further protonated using deuterium plus, producing CH3D molecule and giving back this bis aqua chloride platinum plus complex, which can again activate a methane molecule. So, what she will have attained is a catalytic CH activation cycle. So, why this is CH activation cycle? So, what we see is that CH more molecule is entering the cycle and it is getting cleaved as H and CH3, and that CH3 is trapped with deuterium. So, the CH bond is indeed getting cleaved, and that cleaving is happening via the initial agostic interaction. So, she will have attained successfully this catalytic CH activation cycle. But what is more important in this is the next step where he achieved CH functionalization. So, this was CH activation and she will have achieved further CH functionalization. And that is obtained by treating this aqua chloroplatinum complex with this platinum 4 compound PtCl6 2 minus. So, this is a platinum 4 compound, and this catalytic cycle is all done with platinum 2 compound. So, upon treatment of this platinum 2 methyl with this platinum hexachloro platinum 4 compound, that leads to this platinum 2 compound where this methyl get exchanged with the chlorine. This is a platinum 2 compound and it produces alongside this a platinum 4 compound So, this is a platinum 4 compound and this for this reaction this platinum 4 compound is used in stoichiometric amount. So, this was a catalytic cycle and this platinum 2 was treated stoichiometrically with platinum 4 compound leading to this platinum 4 compound which is platinum pentachloromethyl. Now, this platinum pentachloromethyl when treated with water produces platinum 2 compound plus HCl and this methyl gets hydrolyzed to give methanol and this platinum 4 compound also decomposes to give platinum 2 compound along with CH3Cl. So, what is interesting is that CH bond of methane has produced methanol as well as methyl chloride, which is CH3Cl. So, Shilov has selectively converted methane to methanol by replacing the hydrogen with hydroxide group, and also it could convert methyl CH3H to CH3Cl, where this hydrogen has been replaced by chlorine, and it has done by two steps. One was this catalytic CH activation, followed by stoichiometric CH functionalization, and this shows that these compounds are of tremendous use, whereas a inert compound like methane, which has very strong CH bond, can be made into useful value added chemicals in forms of methanol and methyl chloride. So, with this, let me summarize the discussion on today's topic. What we have discussed today is we have looked at the intermolecular CH activation, and then we have taken a pioneering example whereby intermolecular CH activation was converted to CH functionalization, and this work was done by Shilov, who had done the CH activation in a catalytic fashion and then followed it up with CH functionalization in a stoichiometric fashion, and thereby could functionalize methane to methanol as well as methyl chlorides. And another interesting thing that we had discussed is that CH activation, catalytic CH activation was performed in a catalytic fashion, as I mentioned, by catalytic CH activation, whereas CH functionalization was done in a stoichiometric fashion. Also, CH activation was achieved with platinum 2 complexes, CH functionalization was achieved from platinum 4 complexes, and that shows the utility of this method and versatility of platinum as a metal, because in two different oxidation state it can perform two interesting reactions. Now, with this background, we are going to take up something very interesting in next lecture, that will discuss more examples of these intermolecular CH activations, the ones that followed after Shilov's work, and also would be very useful in terms of understanding the chemistry of this kind of complexes. So, I look forward to take up this topic in the next lecture. Until then, thank you.